Welcome to the Part B lecture notebook for the second module on Python basics. In this lecture notebook, we will learn what a library is and what libraries are used for. Sometimes libraries are also called packages. We will see how to load a Python library and use its functions and library constants. And this will enable us to get familiar with the so-called dot convention within Python. We will also understand what the shape of a numpy array means and how to create arrays of different shapes. And then we will also see how to cast the data type of a numpy array, which ties the contents of this notebook back with some of the things we saw in the Part A notebook involving different types of data and how to do casting. So there are 3 activities for you to do, as well as some instructional-led activities that I will do within this video and that you should follow along with on your own. The third activity, of course, is a summary, as is the case in all the notebooks, starting in Module 2, moving on in this class, in the lecture notebooks that is. And we will just go ahead and get started. So we begin with the discussion of how to import packages, which are sometimes called libraries. We will also touch upon sub-packages and modules. This video will play here once I replace this link with the one from this current video that I am making now. So some key points. A module, you will sometimes hear me refer to the concept of a module in Python, and you will have to create your own user-defined module starting in the 3rd module of this course. A module is simply a single file of Python code that is meant to be imported. A package, on the other hand, is a collection of Python modules under a common namespace. What that means is a namespace is a set of symbols that are used to organize objects of various kinds so that these objects may be referred to by name. You will see the example with numpy in this lecture. Now, unlike many scripting languages, Python actually follows the conventions of many compile languages by accessing packages, also known as libraries, via the import statement. 3 of the libraries you'll find yourself importing often within this class are numpy, scipy, and matplotlib. We will primarily be concerned with numpy in this notebook. You will see elements of scipy later. That's used a lot in scientific computing, and matplotlib is used for visualizing results. As the plot might indicate, you're plotting. So we'll see matplotlib later in the module 2 in a future notebook, lecture notebook within this module. I provided links here for you to click on and see some of the details. There's also quick start tutorials to things like numpy that you might want to look at and take time with. Same thing with scipy. There's also an introduction, a scipy tutorial here to go through. So there's lots of great things that you can go through and make your own notebooks for your own reference, looking at some of the details that we won't have time to study in this class, but I try to give you time to do, and I factor in some of that time when I say that this might take 3 hours. I'm including watching the video, going through it, but also doing your own exploration through the links and tutorials and looking at code and other things online. So let's go ahead and get started. We're going to import numpy. When you import numpy, just like this will import numpy as numpy. So I'll go ahead and run it and move on to the next cell with my Shift-Enter command. Now, numpy is now imported into the namespace. It's now taking up some memory. So if we want to start using things in numpy, we are going to use the dot convention, where you use the library name, in this case numpy, and then we'll have a dot followed with either function names with the arguments in them, or library constants such as the pi or e constant that you might be familiar with from other math courses. So here in this next code cell, what I show you is pi is actually a library constant within numpy, your standard 3.14 approximately value, and we can look at what the type of that is. This is a float type, so I'll just go ahead and run this here. So we have an approximation to the number pi, and we see that it's of type float, which isn't surprising because it's 3.14159 and so on. And then we can compute sine of pi by using the sine function within numpy. That's a math function held with that we have access to within numpy, and we can pass it the pi constant. So this should be about 0 because sine of pi is 0. But now you see it's not exactly 0. This again is the issue with finite precision arithmetic on a computer, numbers like pi, which are irrational so that there's never a repeating or ending set of decimal points. It just goes on and on and on forever in no pattern. There's no repeating pattern in it. But it can only be stored to some finite amount of digits. And so when you evaluate the sine function, which is itself something that's approximated on the computer, you don't get something that's quite zero, but you get something that is on the order. The way to read this number, e to the negative 16, e minus 16, is this is like about 1.2 times 10 to the negative 16. That's how you should interpret that number. So that's approximately zero. That, as far as the computer concerned, is 0.0000. You got like 15, 16 of these zeros here, and then you get the 1. Okay. Important note about autocomplete. In an interactive environment, such as an IPython terminal or a Jupyter notebook, such as this environment we're working in, autocomplete features exist for imported objects. So what I suggest here is that you type in numpy with the dot, and then you press the tab key on your keyboard. So I'll do that now. If I say numpy and then dot, it's important to have the dot. Now when I press tab, it might take just a second to load, but you'll see here's all the options I have within numpy, and you see there's a lot of options. So this means I don't have to remember everything, or I don't have to necessarily look up documentation. I can just find the thing I want. For instance, let's try to find the sine function. I went right by it. There's our trigonometric sine function, whereas this is a different function, sine. And maybe I want to look at that and say, what does that do? And I could try it on the pi constant. And, I skipping a step here. It's numpy. There we go. We see that the sine of pi is positive, so it will return a value of 1. Whereas if I gave it a negative value, it would say negative 1. So the sine function just returns the sign, the sign, the positive or negative. It lets you know whether or not the input is positive or negative. What happens when you give it, let's say, 0? The 0 has no sign. It's neither positive nor negative. So anyways, you can... Also, I want to show this before I move on. Let's say I was looking for functions or things that were available within NumPy that started with the letter C. So I could start typing the letter C, and now when I press tab, it's only the things that start with C. And we can see that it is telling me what these things are in terms of classes, instances, which would be like functions, other modules. Here's functions, classes. It tells me all the things that are in here. So there you go. Or if I just press tab and then I started doing, I started typing letters, let's say F and then L, right? It's going to start narrowing down the options that are available to you that start with F and L. I guess in this case, not just start with F and L, also have an L in there. It's a rather flexible search. So we just see everything with F's and L's there. And then you can just click for whatever you want. So that's something for you to play with just a little bit to get the sense of how the dot convention works. Now you might ask, what if we just want to import a particular function or subpackage? So we might only need a very specific subset of functions or a subpackage within a large package like NumPy. You may then only want to import those parts of the package you need in order to make your code more memory efficient. NumPy, SciPy, Matplotlib, these are all large packages. And if you're trying to make your code very efficient, you only need, let's say, three functions from these packages, you'd only want to import those functions. You don't need to import the entire package. So I'm just going to show you an example of how to do that in case this was something you're interested in efficiency. So I will import the log function from the math package and the random subpackage from NumPy to generate a single sample from a normal distribution by taking the logarithm of a log normal sample. So I'm just doing this not so that you necessarily understand all that I'm doing, although I provide a link here so you could try to read about a log normal distribution. This is only intended to show how you can combine multiple imported functions and subpackages. So I import log from math. So to do that, I say from math, import the log function. So this doesn't import the entire math library, it just imports the log function from the math library. And then from NumPy, I can import random. Now NumPy is already imported, but I'm showing you again, this is just a use case, how you might import the random subpackage from NumPy. Then now that I have these, I can generate a single sample of a log normal from a normal distribution by taking the log of a log normal distribution. So here is my random.logNormal call. So within random, I use the dot convention in that sub-library. And I call the log normal function to generate a single log normal sample. I then take the log of it, and we can see the output. And I see it's 1.364. Now this is random, so every time I rerun this, I'm going to get a different output, right? 1.98. So you see it has this randomness to it because it is a random subpackage. So this leads us into our first instructor-led activity. We will have some practice with using imported functions. So you are to, let's read the instructions carefully because these are pretty much exactly like what you have here, although I ask you to do something with a different random number generator for your activity. For mine, I want to first fill in the missing pieces of the code cells. Notice I said cells, there's 2 code cells here, to import the normal function from the subpackage numpy.random as our norm. Now this is a little different. I don't want to import the entire random subpackage. I only want to import a function from the subpackage. So this is showing a different use case. From numpy.random, I want to import normal, and I want to import that as our norm. So that's it. That's all you have to do to import a particular function from a subpackage of a larger package. So this uses the dot convention. I then import the normal function, and then I'm saying exactly the type of name I want to call it. It's because maybe I don't want to say normal anymore. I want to emphasize it's a random normal. So I say our norm for random normal. So now with that, I can run it. That's now run. It generates no output other than to import this into memory. And so now there's this other part of the code, but let's read the rest of the instructions. I then want to print a single normally distributed random number with mean 0 and standard deviation 1. I also want to print a single normally distributed random number with mean 5 and standard deviation 0.1. And I point out you may find it useful to first look at the documentation on this normal function. So here is a good place actually for you to try to pause this video, click on this link, and see if you can finish the rest of this instructor-led activity before continuing with the video to see me do it. All right, I will show how I would read this documentation. When you click on the link that I provided, you see that the numpy.random.normal function, the normal function within the random subpackage within the numpy. That's the way you read it with the different dots, right? There's first dot gets me into the subpackage. The second dot is telling me normal is within random, which is within numpy. It has a location and a scale variable that I have to assign. The location variable, LOC, the loc variable, says what the mean of the distribution should be. The scale tells me what the standard deviation, the spread of the width of the distribution should be. And if you look down here, there's more notes about this. The documentation is quite useful, and they even have examples to show how to do things. So, and there's even something involving matplotlib and how to generate some plots involving many random draws from a random distribution. So there's a lot of things for you to play with and explore just by looking at documentation. You can try their examples and get a deeper understanding of how to use various functionality. So we know location is supposed to be the mean. So 0.0 is what the first one's supposed to be. I also have this in the code comments here as well as in these instructions. And the scale corresponds to the standard deviation, which is supposed to be 1.0. Now if I try to run this, it will generate an error. If I just make those, let's see what goes on. Line 10 is an error. Now there's multiple lines here, so we can go to edit, view, and we can say show line numbers to make our lives a little easier. And we say there's line 10. Oh, we haven't set the location or scale yet for the second sample we want to draw, which is supposed to have mean 5 and standard deviation of 0.1. There's a syntax error because we have location equal and then we didn't assign anything. We had a comma. So it says that's an invalid syntax. You can't write that. You need to actually assign values to this location and scale. So we'll put 5.0 and 0.1. Now when we run this, we see that we generate our random sample from a normal 0, 1 distribution, a standard normal distribution, and one where we move the distribution to a mean 5 and we reduce the standard deviation so that more of the samples are closer to the mean. And you can see this by rerunning the code cell multiple times. So if I run it again, you see this one changed to -2, and that might seem like quite a deviation away from 0, but it had a standard deviation of 1. This standard deviation of 0.1 will constrain that variable. You don't necessarily need to understand that, as opposed to just develop an appreciation for how different variable these samples can be upon rerunning this multiple times, and that variation is due to the difference in what we said the scale variable was, which again, when you go to the documentation, we see that the standard deviation describes the spread or width of the distribution. So that's going to say how far things move away from the mean value. So you're really just meant to input these values and get this to run. You don't necessarily need to understand everything about random number distribution. I'm just showing you a use case. Now I ask you to do this here. You'll notice it's very similar instructions, except what I ask you to do is fill in the missing pieces of the code cells below to now import the uniform function from the subpackage numpy.random, and you're supposed to import it as runif, a random uniform number generator. And if you should click on the link there and read about it and see what low and high do in terms of the setting boundaries on things. So that's for you to do. Hopefully it only takes a minute or two for you to do that activity. And then moving on, we can also import a library and assign it a convenient nickname. And I point out, this is actually how we typically do things. And by we, I mean the community of Python programmers. So typically when you look up documentation, you will see that people import numpy as np. For instance, when you go to this documentation on the random uniform, you will see that they're using numpy as np. They're assuming you've imported numpy already as np. And you're seeing it everywhere. There's just np. As well with the random normal values, they also were assuming that you've imported numpy as np. So even the documentation, the official documentation, is assuming that you've done this. This is the most common way that numpy is imported in Python code. So I will import it, and then I will show that you can then access with the dot notation, the dot convention, the same things. And so here I'm going to use a log function within numpy and evaluate it at the constant e, which should produce a value of 1, which it does, 1.0. And one of the things to realize is that when you've imported libraries, they take up space in memory, just like variables you create. And so if you remember the whos command from the previous lecture notebook, this magic command with the %time in front of it, we now see all the things we've imported. We've imported the log function from math. So this is now a built-in function that we've imported from math. We've imported numpy and numpy as np. So it created two different copies of numpy. So this is not efficient. We're taking up memory, twice as much memory as we need to have both these things in there. We've imported the random subpackage. We've imported the normal function from within the random subpackage of numpy as our norm. And we've created variables, float variables called sample. And we've rewritten it several times in here. And you will also just use the same variable name in here. So those are all the things in our memory, but the important thing to realize is our packages have a type of module. Now, there's a cautionary note on importing that you should really read carefully. And I seriously mean you need to read this, because you may come across very poorly written code. It is possible. There's a lot of information out there. And you might see people that import entire packages as star. That will simply dump everything into memory, and then you don't need to do numpy dot anything except for subpackages. You would have to still do random dot, but you don't have to do numpy dot random if you do this. If that doesn't make sense, don't worry, because what I'm saying is you should never do this. Don't ever do this. No, 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 no. And I say why. I give you 3 reasons. Please read this carefully. I repeat them as key points because I really want to emphasize you should not do this. So I don't want to dwell on that, other than you should read those reasons very carefully and understand, hopefully try to understand them. And if you don't understand them, just know you should not do this. Don't ever do this. Now there's also a help function within Python, and you can even look at help of help. This simply will read in doc strings from the packages, and we'll get into doc strings in a later lecture, but it will give you useful information if maybe you don't have internet access or it's unreliable internet access. Generally, if I have internet access, I look at the official documentation, like what I was showing here for packages to get examples and information, but the help is sometimes useful within here. And so if I do even help of help, this will tell me things about what's going on in the help function. And it will often sometimes provide links elsewhere. So you could import, you can edit these as you see fit. You could look at help on numpy, and I've already imported as np, so let's look at help numpy. Oh, this is too big. This is too much information within that. So the help command in some sense has its limitations as well. So my data rate was exceeded there. NumPy has too big, but maybe I can look at the random subpackage. There we go. Help on the package numpy.random. So numpy, the help file, there's just too much information for it to read into the screen. But look at all this information on random. It has all this information here that you would also find on the web page. So the web page is better, and you'll notice this is now a huge amount of information. I don't want to scroll through everything here, but you can play around with the help command. I think generally there's another way where you can do a question mark before an object. Yeah, and it can also produce some outputs. So there's other ways to get help using a question mark there. We're just going to go ahead and delete that. But play around with that. See how you can use help files, or you can access help files within your notebook. Now to the real reason we care about NumPy. We like NumPy more than list when we deal with any kind of scientific computing. Why? Well, they're more efficient than lists of numbers. They're more convenient to use when we need to perform operations from numerical linear algebra, and much of computational and data science boils down to numerical linear algebra. And what do I mean by convenient? We get a lot, and I mean a lot, of vector and matrix operations for free when we use NumPy, which means we can avoid the unnecessary work that would be required if we were to just use list, like having to define our own functions to carry out the operations we want. You might recall from the previous lecture notebook that if you took a list and multiplied it by an integer, you just got a longer list that copied the entries of the list over and over and over again, however many times you multiplied whatever the integer number was. But if you actually wanted to multiply that integer to every component in the list, you'd have to write your own function to do that. You don't have to do that with NumPy arrays. Now, does that mean lists have no advantages? No, lists are very flexible objects. They can handle multiple different types of data within the list in a way that a NumPy array cannot. But this flexibility comes with a heavy price in terms of memory usage and not being able to apply a lot of built-in functionality on the list that are very useful for computational science. So basically, NumPy arrays and lists are both useful in different contexts, and they're both preferred in different contexts. NumPy arrays are typically either 1, 2, or 3-dimensional, and this is determined by the use of a certain number of square brackets, and you see I'll show you an example below. A particular entry in an array is commonly referred to as a component of the array. Now, a 1D array has a shape of the form, when you print out the shape, I'll show you the examples of this, you'll see a parenthesis, and then you'll see a number, an integer, and then a comma with nothing. That's a 1D array. There's no additional information other than how many components are in the array. A 2D array has the shape n comma m as a tuple. Now, where n is going to denote the number of rows, m will actually denote the number of columns in the array. A 3D array is best thought of as having the shape k comma n comma m, and I write that so that when you think of it, you can think of it in terms of copies of 2D arrays, or not necessarily copies, but a tiling of 2D arrays. It is best conceptualized as k distinct or different 2D arrays, each of shape n comma m. So we'll see this below. This is a 1D array. Notice that there is a single square pair of square brackets here. Now, a 2D array might have multiple pairs of square brackets, but it will have one outer pair of square brackets shown here. Notice it's highlighted in green. And then all inner pairs of the square brackets will denote the individual rows of the array. So this is an array that should have 3 rows. And it should have the first row be 1, 2, the second row be 3, 4, and the third row be 5, 6, which means its shape should be what? 3 by 2. Now, if you look at this array, this is a 3D array, there are 3 sets of brackets. And there's always just one outer set of square brackets. And then you'll notice that there's inner sets of these second square brackets. That's indicating how many 2D arrays you have. So you should notice there are 2 of these 2D arrays. And each of these 2D arrays has 2 rows with 3 columns. However many columns are in there are going to be determined by the number of entries you see there. So that looks like it should be of what shape? We have, well, let's go ahead and do it. Let's run this, and I actually just print some outputs of the arrays. And here I'm showing some indexing. And now I'll actually print the shapes so that we can study these a little bit more carefully. So we see that array 1, which had one set of outer brackets with 4 entries, is of shape 4, then nothing. It's not a 0. There's nothing there. The second array is a shape of 3 by 2, which is what we expect. It's 3 by 2. And that third array, the 3D array, is of shape 2 by 2 by 3. It is as if you have 2 2 by 3 arrays. That's the way to think of this. There's 2 different 2 by 3 arrays. And the first 2 by 3 array has a row 1, 2, 3, and then a second row 4, 5, 6. The second 2D array, which is what I printed here, because remember Python indexing starts at 0. We saw that with lists. So the second 2D array has a row 7, 8, 9 and a second row 10, 11, 12, which is exactly what was printed here. So that's how to interpret this. Now you could go and change this. You could make this a 0 and print it. And you see this is array 3D 1, 2, 3, 4, 5, 6. Actually, I should change this, and I'll update this here. I'll make it so that it looks more like what I will give you in your notebook. There we go. That component of it. Now, if you wanted to print the entire array, you could do this. And now you see the 2 copies of the 2 by 3 arrays. Here's the first 2 by 3 array, and notice how when it printed, it put a space here before the next 2 by 3 array, before the next 2-dimensional array. You might have to rewatch that part of the video a few times. The shapes, especially with the 3D shapes, can seem a little tricky, and it takes a little bit of practice to get used to it with these multiple brackets. So there's an additional different 3D array I provide here, and before you even run this code cell, I would say look at this and let's try to examine what we think the shape will be. So we see first there's that outer bracket, and then we see that there's 2 pairs of these next sets of inner brackets. And now when we look at this, we say, oh, each row has only 2 columns, and now we see that there's 3 rows in that first 2D array, and there's also 3 rows in that second 2D array. So this should look like a 2 by 3 by 2 array. We print the entire array. Here's 2 copies of 3 by 2 arrays with 3 rows and 2 columns. So there it is, the shape 2 by 3 by 2. There's 2 3 by 2 arrays is the way to think of that. Now here's an instructor-led activity for actually creating our own arrays. I'm going to fill in the code cells below to create a 2D array of shape 4 by 2 and a 3D array of shape 2 by 4 by 2. Now, in your activity, you'll have to do different shaped arrays that are 2D and 3D. I ask you to do a couple of them. So just read the instructions, but you might want to pause the video now and do this on your own, and then watch from here on out to see me do it. Okay, I'll now do it. So the 2D array is supposed to be of shape 4 by 2. The entries do not matter, but we'll first set up our outer array. Now we set up each row. We're supposed to have 4 rows with 2 columns. So we might say, here's our first row. Whatever values you put in here do not matter. I'm just counting up with integers. So 5, 6, and then 7, 8. So there we go. That set of entries should have produced a 4 by 2 array. Let's see if I did this correctly. Here's my array. I see 4 rows with 2 columns, and I see that my shape is correct. Now I need to make a 3D array of shape 2 by 4 by 2. And if you're doing this in stages, you might want to pause again and do that, or just watch me here. So I need, what was the shape again? I've already forgot. 2 by 4 by 2. Okay. So we need our outer, we need our inner, and we need our innermost. And we need how many 2D arrays? We have 2 4 by 2 arrays. Okay. So I'm going to go ahead and just set it up like this. So now what I need is I need to set up here. There we go. Let me set it up like that. Notice what I've done here. And I'm going to create some spaces so that it's easier to follow along the structure. Sometimes it's nice to get the structure in place before you put in the components when you're building your arrays. This will be my first 2D array, right? So within that, there's supposed to be 4 by 2. So I'm going to have 4 rows within my first 2D array. And I also need 4 rows within my next 2D array. I will now input values. So 1 and 2, I'll do it in a bit of a efficient way with the spacing. 3, 4, 5, 6, 7, 8. And I'm actually going to press enter so that I can do this on a next line. And it just makes it so I don't have a really long line of code. You can do that kind of line break after a comma, and it will continue with inputting everything. Notice how that parenthesis still turns green, so it's still connected to this line of code. It's just a continuation of that line. So now 9, 10. Again, I'll try to just not do too many spaces in the interest of space here. And then there we go. So let's see if I did this right. Did this create a 2 copies of 4 by 2, or 2 different 4 by 2 arrays? If I run it, it looks like I have a 4 by 2 array and a 4 by 2 array, and it's of shape 2 by 4 by 2. So I've done this correctly. So you're asked to make your own arrays of different shapes that I'm asking you to make them. So this is for you to do. Hopefully that just takes a few minutes, but it might be a little bit of trial and error. And you'll notice I already set up some of the initial set of brackets for you to fill in, but you might need to edit these a little bit. So first, notice that these 2 cells are for you to fill in the code cells to create these 2D arrays of shape 1 by 2 by 3. Then I ask you to create new code cells to make a 3D array of shape 3 by 2 by 1 and a 2D array of shape 3 by 2. So if you have to read that carefully, I'm asking you to make 2 more code cells, and for you to perhaps copy and paste the info from these code cells into these ones, so that, but then edit them to make arrays of different shapes. That's what I'm asking you to do. But I'll go ahead and delete that. That's for you to do. Now let's talk about casting the type of a numpy array. The numpy data type attribute dtype describes the type of data. Data type, dtype. You'll find that a lot of functions and variables are named very sensibly within Python. So it is cast as the minimal data type required to store all the data. So if you look at our 3D array that we've created before, that I created above, it had nothing but integers. So the type of numpy array is the minimal type required to hold all the data. That's what I printed out here. So if you look at this, it says, well, they're all integers, so it stores them as an integer type. So now if I look at the 3D array and I just change one entry, I make that 12, that was the last value. If I make it 12.0, so I'm going back to my original 3D array and I'm taking 12 and turning it into 12.0, only one value is now a float. But if I look at this array, look at the entries, they all have a period next to them now because they're all floats. They're all float types now. I printed the data type as a float. So if as soon as one value is a float, if everything else is an integer, it will actually end up being treated as a float. Now, you can recast the data in a numpy array as a different data type using the special asType function. So I'll show that here. That 2D array, I could cast everything as a float. So here's a copy of it. But that only did it in the instance it was called. It didn't actually change the entries in the array. They're still left as an integer type. So you can see it here, the D type of that was printed as an integer right there. And then I could also turn everything into a string, for instance. So here's all the entries, and now you see they have tick marks around them to indicate that it's an array of strings. Excuse me. You may also specify the data type during the creation call. So imagine that I have all these entries, and they're mostly integers, and I accidentally hit a period somewhere, and there's a lot of entries, and I don't want to necessarily go back and edit. I can simply say everything should be treated like an integer, and then when that gets assigned to a variable, it's no longer a bunch of floats, because everything was treated as an integer at the time of creation and assigning it to this variable. So the data type is of type int. So that's the end of the recording, because the last activity is now for you to do a summary. Create your summary points. You have to fill them in here, and you have to fill in code examples that go along with your summary points. Remember to write in complete sentences and show examples that are relevant to what you're saying you have seen or learned in the notebook. And of course, you can have more than 3. Thank you for listening, and I'll talk to you in a future lecture.